In the last video we looked at infinite series, and we left off by saying one of the hardest parts of them will be determining how to find these series sums, and to do that we need to determine the convergence first. So we're going to be looking at a lot of different tests to determine convergence. So one of the easiest types of series is something called a geometric series. Geometric series, we're going to be able to determine fairly quickly whether they're going to converge or diverge. So let's first define what a geometric series is. They're a series of the form a plus a times r plus a times r squared plus a times r to the third, all the way up till we have a to the r to the n minus 1 plus, and then of course they keep going, where a and r are just fixed real numbers. So we can write that more concisely using our summation notation. Summation n equals 1 to infinity of a times r to the n minus 1 power. So we have a coefficient times a number being raised to a power. So this is essentially a sequence of exponential numbers with the same base, same coefficient being added together. That is what we're looking at. They do need to be the same base, the same coefficient, otherwise it's not a geometric series. And also notice the index, summation, and the exponent in this series. The index starts at 1 and it goes to n minus 1. That is important. That is necessary for this to be a geometric series and for formulas later on to work. I should note that doesn't mean it's not a geometric series if they're not right, but it means the formulas that we're going to develop are not correct. And so we might have to do a little manipulation, and we'll see examples of that in this video. But it is very important, before we go using our formulas for these convergences, to determine is the n equals 1, does the index start at 1, does it go to an exponent of n minus 1. So what I want to do now then, to determine if the geometric series converges. So let's first let r equal 1. So when does this geometric series converge? Well, if r is equal to 1, then we would have the series a plus a plus a, because all these r's are just 1, it's always going to be just an a. So what we're getting here is we're taking a and we're multiplying it n times for the partial sum, where we're going from a to the 1 minus a times 1 to the n minus 1. The r's are always equal to 1. So if we look at the limit of this thing, the limit as n goes to infinity of this partial sum, a times n, that's equal to infinity. So this diverges. We cannot allow the r to equal 1 if we want the geometric series to converge. Next, let's look at r equal to a negative 1. Well, in this case, we would have the partial sum equal to a 1, because we'd start off with an a, we'd start off with a positive 1a, or just a. Then we'd have a minus a, because we'd have the r is a negative 1, that's a negative a. Then we'd have a negative 1 squared, that turns it back into a positive a. Then we'd have a negative a. We're going to do this over and over again. And so what we're seeing is these are continually flipping between being equal to a or 0. So these are equal to a or 0 depending on where we're stopping. And so again, this is not converging, this is diverging. So if r is equal to negative 1, we have another divergent series. What if our r value is less than 1? And what if the absolute value of the r value is greater than 1? We'll consider the positive and negative case, and then we'll talk about what happens. We'll consider strictly the positive cases, greater than 1, less than 1, and then we'll talk about the negative case. So for this, let's consider our sequence of partial sums, a plus ar plus ar squared plus, let me scoot over a little bit, all the way up to ar to the n minus 1. Let's multiply both sides by r. So we'd have r times the partial sum be ra plus ar squared. Let me flip this around just so I'm consistent. Ar times plus ar squared plus ar. Really, I need some dots in here. That was the next term. We'd have the cubed plus ar cubed plus all the way up till we get to a to the r to the n now, because we've multiplied this r to the n minus 1 by r, so now it's just r to the n. So let's subtract over something here, because what we realize now is that this all was just equal to the partial sum minus the a r to the n, because that wasn't there before. We have this extra a. We have an extra a in here. Well, we're lacking an a. So s to the n minus r to the s to the n, meaning we're taking the initial partial sum, subtracting off this thing. Everything's going to cancel except for the a minus a r to the n. Taking the sum, subtracting itself, so we're subtracting these two things. Sum minus this new sum that we've created will give us this expression right here. And now let's do a little factoring. So we can factor out the s sub n, and that would be 1 minus r. And we can factor out an a, and we'd have 1 minus r to the n. And now I'm going to divide by that 1 minus r to the n. Divide. And so s to the n is equal to a 1 minus r to the n over 1 minus r with no exponent. And so now we have the ability to find the sum for the geometric series as long as the r is not equal to 1. Why is it that we can't allow the r to equal 1? Because we see that we're getting a 0 down here in the denominator. And again, we're considering this if the absolute value is less than 1 or greater than 1. So we've kind of ignored the fact what happens if it's equal to 1. So now we have a formula for the partial sum, and we can use this. So let's look at if the absolute value of r is less than 1 in the partial sum. Well, then what we're saying is we want to know what happens to the series, and the series is infinite. So we're looking at the n as it goes to infinity of a 1 minus r over n to the 1 minus r to the n over 1 minus r, because this is the partial sum for the nth one, and we want to know what happens as that n goes to infinity as the series continues to increase. And so if the r is less than 1, that means we have a fraction here, and that fraction is going to infinity. The fraction is being raised to the infinity power, which means that is going to a 0. And so we'd be left with a times 1 over 1 minus r. So if the absolute value of r is less than 1, this is our series value. That will be equal to the series value. If the absolute value of the r is greater than 1, well, now we're thinking about the limit as n goes to infinity of a times 1 minus r over n, r to the n over 1 minus r. Same thing, but this time, because this is going to infinity, this piece is also going to infinity. R is greater than 1, that's going to infinity, so we'd have 1 minus infinity. And so that thing is diverging. It would be going to infinity. So what that tells us is if the absolute value of r is greater than or equal to 1, the geometric series diverges. The only time that the series will converge is if the absolute value of the r is less than 1. The geometric series converges and has a sum of the a over 1 minus r. Geometric series are really nice because anytime we see that we have that coefficient times a number being raised to a power, we have a formula for its sum. We can figure that out very, very quickly. So let's determine, as an example, so this is an example, let's determine what / if the series summation -2 to the n times 7 over 5 and is equal to 0 to infinity converges to. Right, so the first thing that I recognize here is that this does not match up with the geometric series that I was told, right? We were told a geometric series is a series k equals 1 to n of a to the r to the a times r to the n minus 1. And we have a starting point of n equals 0, and our exponent is n, and I meant that to be a 5 to the n. So if you would change that in your notes, 5 to the n, I need this, I would like this to work out in a certain way. So the first thing I'm going to do is I'm going to rewrite this series by changing the index of summation. I want to change that index to n equals 1. So if I'm forcing the n forward here, I have to force it backward by 1 here. So I can write this as negative 2 n minus 1 times 7 over 5 to the n minus 1. We can always change those indices. Think about if we had n equals 0, these would have started off as 1s because this would be n to the 0. So I still need this to be a 1. I still need this to be a 1. So by forcing this up to n equals 1, now we have the n minus 1, which is still 0, giving us a 1 here and 1 here. So we can change those indices, and sometimes we need to do that. That is a necessary step. Still doesn't quite look like the geometric series that I wanted, because I want it to be one number to a power, but notice the 2/5, they're both raised to the same exponent. So if I want to, I can bring them under the same exponent. Now actually there is a geometric series that says if your summation starts at n equals 0 and goes to n, that is still a geometric series. It is equivalent to what the formula I wrote at the top of the screen was, the start of the video. So you don't have to make this step here, but we do need to put this together into one fraction. Whether we're using the n with the n equals 0 or if we're using the n minus 1 with the n equals 1, we need to put that together as one fraction. Had it not been that when we changed this to n equals 1, we had an n minus 1 here, we could not have used the geometric series directly. We would have had to have thought about some other steps we would need to use. So it does need to be the index starts at 1 and where our exponent is n minus 1, or the index starts at 0 and we're going to n. We need to have that one number raised to the same power. That is necessary. Otherwise, we need to tinker with this a little bit more. So now let's think about this. What we've just said is if this r value, the number being raised to a power, is less than 1, or if this absolute value of this r, which in this case is negative 2/5, if that absolute value is less than 1, which is true in this case, this must converge. So we know that the r is equal to negative 2/5, our a is equal to the 7. Remember, the a is simply the coefficient, the number not being raised to the power, so let me get back up to my definition. The a is that number, the coefficient, thing not being raised to a power, so our a is equal to 7. And so now I can just simply use my sum formula, the a over 1 minus the r being negative 2/5. And so our series of n is equal to 0 to infinity of negative 2 to the n times 7 over 5 to the n has to be equal to this sum right here, and it would be 7 over 7/5, which when we multiply that by the reciprocal would be 1/5. That is going to be equal to our sum. So we can actually find the sum for this one because it does converge. That is what our series is equal to. We know exactly what it converges to. And say that is what it converges to, or that is what the series is equal to. Let's take another example. This one's going to be a little bit different. Determine, or let me change that. Express the repeating decimal .030303 continued as a ratio of two integers. All right, so this one doesn't look like a geometric series, but let's break this down. Let's really take a look at it. 2.030303 continued. It's really equal to a 2 plus 3 over 100 plus 3 over 100 squared, because it's the next two decimal places, plus 3 over 100 cubed because it's the next 2 decimal places. And we can see that there's a 2 here, but then what we also see is that this is simply equal to the summation n is equal to 1 to infinity of 3 over 100 to the n power. We have 300 to the first, 3 over 100 to the first, 3 over 100 squared, 3 over 100 cubed, so forth. Continues to repeat. And that's beginning to look a lot like the geometric series. Sure, we have the 2 sig in front, but that's looking a lot like the geometric series, but it's not quite. Because remember, we said that the index, if it starts at 1, the exponent has to be n minus 1. And this is not an n minus 1, it's an n. And so we're going to need to manipulate this a little bit. So what we can do is we can express this as 1 over 100 times 3 over 100 to the n minus 1. Because remember, we can, if we're multiplying like bases, we think about adding their exponents or just factoring out that 1 over 100. And I can pull that to the front of my summation. 1 over 100 times the summation, n equals 1, 3 times. The other thing I might do, just because we like to see the a times r to the n minus 1, is I'm going to write this as a 1 over 100 to the n minus 1. Remember, if you have something in the denominator with nothing in the numerator being raised to a power, you can always think of it as a 1 over, because that is there is always an understood 1 above numbers like that. So now we have this expressed as a geometric series, and so we know that that has to be convergent, and we also know what its sum is. We know that that sum is equal to 3 over 1 minus the r, which is 1 over 100. And so we can do a little simplification here. We can write this as 2 plus 1 over 100 times 3 over 99 over 100. And when we simplify that, we get 1 over 33, because the hundreds would cancel. The 3 over 99 would give me 1 over 33. And so we can write this as a fraction 67 over 33. So what this allows us to do is to turn any repeating decimal into a fraction. We know exactly what its fraction is without the use of a calculator. So repeating decimals, we can rewrite this as fractions using geometric series. That is one of the reasons geometric series are so important. We can see anytime we have these repeating decimals, there is really a geometric series involved. So again, just to remind you that it is very important that index start at 1 and we're looking for the exponent to go to n minus 1. We saw that if the index started at 0 and go to n, that is fine. But if we had an example like the last one where the n and the exponent aren't starting in the correct spot, if the index and the exponent aren't matching in this 1 n minus 1 format, we've got to make some adjustments. And so we can pull numbers out as we did on this fraction here. We can also think about subtracting off terms, because remember, all series are additions of a bunch of terms. And so if we're missing something, if we're missing some lesser terms, we can add in those terms in the series in our summation notation and then subtract them off right behind. So we do need to make sure that our index is starting at 1, our exponent is n minus 1. We might have to do a little bit of work on that. We are looking to get to that coefficient times number being raised to the n minus 1 power. That is very important. Those are some of the most common mistakes, just jumping right into using the formula for the sum rather than making sure that the series actually is in the correct geometric series format.